because I'm speaking on the...
Yeah, I can hear you. I guess everyone else as well. So it's my great pleasure to welcome Zoe Wyatt from Cambridge to the seminar. And Zoe will be speaking about stabilizing relativistic fluids and spacetimes with non-accelerated expansion. So
great.
Go
Thanks,
ahead,
David.
Zoe.
Thanks. And thank you very much to the organizers for the chance to give this talk, because I always love the Central European Relativity Seminar, even sadly if it's not in person. The talk today is based on joint work with David and with Todd, Oliynyk and Monash, and it's based on a paper that actually came out about a year ago, but I have to apologize, this is my first talk ever on this paper. So if I say something wrong or something, please forgive me. So I'm interested in shock formation on FLRW type spacetimes. So in particular, I'm interested in cosmological solutions to the Einstein equations, where in particular, I here allow for a cosmological constant lambda. And typically one considers the cosmological principle, which tells us that the universe is spatially homogeneous and isotropic. So there's no preferred points and no preferred directions. And a consequence of that is that the metric takes what's called a Robertson-Walker form. So we have a time interval I and a maximally symmetric three-space sigma, where the metric then takes this following form here. And so this factor A here is called the scale factor. It's going to be very important in my talk. And we say it's expanding if its time derivative is strictly bigger than 0. So here sigma can, for example, be R3 or H3 or S3 or a quotient thereof, and it has constant sectional curvature. Okay. So the strong symmetry in this model implies that the stress energy tensor takes the form of a perfect fluid. So here we have density, which is only a function of time, pressure, which is only a function of time, and a unit time-like fall velocity for the fluid particles. And if you consider the one of the components of the divergence of the stress energy tensor, you get something called the continuity equation, which is an equation here. Now, the Einstein equations then give you some other equations that determine scale factor. And these are a system of two ODEs called the Fajman equations, which I've written here. And so in this talk, I'm interested in considering a linear barotropic equation of state. So barotropic means that the pressure is a function of just the energy density. And here it's linear because I've got some factor K, which on relativistic grounds needs to be less than or equal to 1. And important cases of this equation of state are those of dust when K vanishes. So there's pressureless, where the pressure is 0, and radiation when K is equal to 1/3. So dust here is describing, let's say, ordinary matter, or cosmologists use it to describe ordinary matter, such as baryons, and radiation is used to describe like a gas of relativistic particles. Okay, and so more generally, we need to have an equation of state relating the pressure and the energy density in order to close this system here of the continuity equation and the Fajman equations. Okay, so it is something that you do need to impose. So it turns out if you integrate up the continuity equation, you get this expression here is actually a constant. Okay, and so you can see here that as the scale factor increases, the energy density rho should be decreasing. So you have a kind of dilution of your fluid, which is will be important later on. And so it turns out one of the Fajman equations reduces using this equation 8 to the following expression here in equation 9. And so I'm interested in the rate of change of the scale factor. And so you can see just from this equation that there's like lots of different dynamics you can have depending on the sign of the sectional curvature, if the cosmological constant is non-zero or strictly bigger than 0, and obviously also the number K. So just to give you some example solutions, one of the solutions is that of Einstein de Sitter, which is a dust universe, so a matter-dominated universe. And here we get a scale factor of t to the 2/3. Remember, this is the scale factor squared here in the metric. And so this is an example of what we call a decelerating, a universe undergoing decelerating expansion. I hope that makes grammatical sense, okay, because the first derivative is positive, but the second derivative is negative. And then another, obviously very well-known example is that of the de Sitter space-time, So here you can take a positive cosmological constant, and this can be obviously supported on different 3 spaces, but here I've just put it on a R3, and here we get an exponential factor here with a factor of lambda. And so this is an example of accelerated expansion since the second derivative is positive. And another final example, which is the topic, let's say, of today's talk, is the Milne universe, which here is in vacuum, but it has a linear scale factor, which means it's an example of 0 acceleration. So the second derivative is 0. So this is all very interesting to give you, let's say, different models of the expanding universe. So, exponential expansion or the Milne-like expansion here. But this was all under high degrees of symmetry. And so the goal is really to understand the stability of particular space-time fluid solutions by treating the Einstein relativistic Euler equations as an initial value problem. And so one of the simpler problems you can do, because this is obviously quite a broad goal, is you could fix the geometry. So you could fix the metric to be a Lorentzian metric, maybe a spacetime may not be, and just consider the relativistic Euler equations. So here I've just written out the Einstein relativistic Euler equations. So we have the 2 equations here describing the fluid, and we need some appropriate equation of state. So as I said, so one problem is, of course, one simplification is you can kind of remove this equation, so just fix the geometry. Another simpler problem you can do is to restrict to irrotational fluids, which essentially means that their vorticity, a notion of vorticity vanishes, and so you can express the forward velocity as the gradient of a scalar field. And when you do this, the relativistic Euler equations reduce to a quasi-linear wave equation for this scalar field phi. Okay, so this is a system of a wave equation that you can study. And so this has been the topic of a lot of research, understanding the stability of solutions to this system of equations. So I just wanted to mention the previous results to really put our result in context. So if you consider a Minkowski background, so where it's fixed, the geometry is fixed, we actually have small data blow up. Okay, this is a remarkable work by Christodoulou, where he showed that shock singularities can form. So the gradient of your scalar field would go to infinity. And this can happen from very, very small perturbations. And these shock singularities will form in finite time. And there was and this is also known outside of relativistic fluids as well. This is known just for the Euler equations. This is a kind of a classical result from the 1800s. So this is perhaps not overly surprising that the same holds true for relativistic fluids. And then there's a paper by Brouwer, Rendell, and Euler from the 90s where they considered a Newtonian cosmological model. So that kind of makes it a bit easier, let's say, than studying Einstein equations. And they considered a perfect fluid either as a dust or with a polytropic equation of state. And they showed that, and the thing I must emphasize is that they considered the cosmological constant to be strictly bigger than 0. And in this case, when lambda is bigger than 0, they showed that small perturbations of some appropriately homogeneous fluid are globally regular. Okay, so you don't get shock formation, which is obviously in big contrast to what happens in Minkowski. Don't forget that Minkowski is an example of an FLRW spacetime, just with the scale factor being 1. However, they also showed that, they also showed that for lambda equal to 0, and in the case of a dust fluid, that small perturbations of your homogeneous fluid solution would lead to finite time blow up. And so in this case, the scale factor is that decelerating example that I mentioned before from the Einstein de Sitter universe. But the key idea to take away from all of this is that space-time expansion can can suppress shock formation in fluids. Yeah, your space-time is expanding, you're pulling apart the fluid lines, let's say, and preventing them from forming discontinuities. So that's kind of the intuition here. And so this has been, as I said, the basis of a lot of research where people have looked at a quiet fluid undergoing accelerated expansion. So the asymptotics of your background are dominated by some cosmological constants. So things are undergoing accelerated expansion, and have shown, there've been lots of results showing global stability with this linear equation of state. So in particular, one of the first works was by Rodnyansky and Speck, and you'll see here a whole host of works looking at different ranges of the parameter K. So here's the radiation case, here's the dust case. And the result of Oliynyk here is the one that is kind of most relevant to our result, because he developed a new method using Fuchsian techniques, which allowed him to treat this parameter range in more generality. And I should just mention, Todd has a recent paper where he was able to consider K above 1/3, which is interesting because there were numerical work suggesting that that wouldn't be true. Okay, so there's all this result in the realm of spacetimes undergoing accelerated expansion. And that was coming from a cosmological constant. And there are obviously other ways that you can induce that kind of behavior. So one such example is what's called a Chaplin gas. So here you have a fluid with negative pressure. And so that's the thing that's kind of pushing apart the fluid and then driving the metric expansion. And so this is also known to be stable in some appropriate irrotational setting. And I should just mention, all these results have, I've done the history perhaps in the wrong way. A lot of these results have been inspired by work of Ringstrom, who was looking at global stability for Einstein scalar field systems. I can't spell the word for, sorry. Where the potential is kind of acting as a cosmological constant. So here, the V0 here was the thing that was essentially giving you, emulating the cosmological constant lambda. And he also was able to treat power law expansion, where again, it needs to be in the case of accelerated expansion. Okay, so you see that really accelerated expansion has been essential to all these papers. And so this leads me to our result, where we considered a fixed metric background, and we call it Milne-like because it doesn't satisfy the Einstein equations, but it's still a Lorentzian spacetime. And so this is it has the linear scale factor of A is equal to T. And so we consider a linear equation of state in this massive case where K is between 0 and 0, and we're able to show that the relativistic Euler equations are non-linearly stable to sufficiently small irrotational perturbations. Okay, so this is the first example of fluid stabilization by space-time expansion, but where the expansion rate is non-accelerated. Okay, so where it's a power law type, but non-accelerated. So yeah, we think that's quite interesting.
Sorry, question.
Yeah.
So you're not assuming any symmetries here for the perturbations, do you?
No. Just,
no symmetries, but decay, I imagine, or not decay either.
These will be.
Oh, you're in a torus. Okay, sure. Okay.
Yeah.
Mm-hmm.
Yeah. Sorry. Yeah. Sorry, I should have. Oh gosh, what did I just do? Okay, there we go. Yes, torus. So yeah, and so I can also put this this result in context with. It's interesting to put it in context with another paper, which is by Speck, who's obviously worked extensively in this area. And so in this paper in 2012, he considered fixed geometry, so fixed Lorentzian metrics of this form and small perturbations of corresponding background homogeneous solutions. And he was interested in deriving conditions on the scale factor to get stability or possibly instability. And so as an example, if you're in the dust case, he needed very strong decay of his scale factor. In the cases in between, he needed some kind of non-negative function here, which is quite important. And when he's in the radiation case, he needed this 1/A to be integrable. Okay, so just a comment is our result is very much not covered by the second case. He's not able to. Our result falls outside of this class that he considers. And something also quite interesting is that Speck was able to show that in the radiation case, shocks would form if the scale factor, the inverse scale factor, was not integrable in time. And so obviously 1/T is not integrable in time. So our result shows that this shock formation here is sharp. This is what he's done here is very much K is equal to 1/3. And so our case here is obviously just outside of that. So that is work of Speck, and there's also kind of related work by Wyatt, which does a similar argument, but for a different equation of state. And so I just wanted to mention a really quick comment on the proof. I don't actually remember what time I'm started. I'm sorry.
You should have 5 minutes.
Oh, okay, all right. Well, I've got heaps of time then because I've gone quite fast. So I just wanted to mention a comment on the proof. So in the case of exponential expansion, your kind of causal domains decouple typically. And so a key insight of Ringstrom, I believe, is to use a localization argument. And so this has appeared in lots of the other works in this area where they can kind of localize to some data in some small region and just understand stability in that patch that emanates from there. And this is something that we can't do because we have such slow polynomial expansion. So we use a method developed for the relativistic Euler equations by Todd Oliynyk. And this is where we transform the equations into a Fuchsian symmetric hyperbolic system. So it's a first order system here. And I didn't really want to go too much into the detail, but let me just mention that kind of the key thing that has allowed us to treat our case is that we allow for these kind of diverging terms here. So I should just say all these terms B0 and these CIs and things like that, these are certain matrices. But in particular, there's a diverging factor here on the left-hand side, which Todd had not considered before. And so including this is what allows us to treat this system. But interestingly, we don't get uniform decay of the solution. So we know that it exists globally, but we don't get the kind of decay estimates that he had in his earlier work on exponentially expanding spacetimes. And so, yeah, so let me just finish by saying that this is what we've shown. So we have global regularity and stability for the irrotational relativistic Euler equations with this equation of state for small initial data in the expanding direction of an FLRW spacetime of this form. Okay, where critically we're in that zero accelerated expansion. And so there's lots of future questions that you can ask with this. So one of these is to, we'd really like the metric to be an actual solution to the Einstein equations and consider the Einstein relativistic Euler equations. So this is work in progress at the moment with David. So we're looking at the stability of Milne as a solution to the Einstein relativistic Euler equation. And something else that is quite interesting is understanding, let's say for power law expansion, so for things of this type where Q is, 1 or bigger than 1, that kind of thing, is understanding critical cases here. So at what value of Q do you necessarily get formation of fluid shocks, and maybe trying to understand that in a bit more detail. So with that, I'll finish my talk. Thank you very much for your attention.
Well, thanks a lot. That was a nice talk. It's always good to hear.
You're biased, David.
about my results from you. No, really. Well, so other questions? Yeah, there's some raised hand.
I've enabled the microphone already.
Okay, cool. So please.
Can I just go ahead and ask the question? Yeah.
Yes, we hear you.
Thanks, Zoe, for the talk. So I had 2 questions. One was I guess for Milne, the 3 space would be hyperbolic, right? Is there a reason why that makes this proof more difficult to consider hyperbolic compared to torus?
I think like Todd's method has just been on the torus, and I suppose in some sense trying to understand how to turn it onto a hyperboloid is going to be quite hard. So I think, in that sense, that was part of the reason, because it was clearly going to take a lot of effort to understand how we could transform his method onto a hyperboloid. I should say the thing that we're looking at here with Milne is using the standard CMC spatially harmonic gauge of Anderson and Moncrief. So I think, and there in some sense it seems to be working out. So we'll just have to see. But I don't think, in some sense, the negative curvature you'd hope would actually help you. Like I think there's a chance that it's gonna. Oh, sorry, that is it. No, I do think it could help you for sure. So it's definitely a question of changing that. I suppose what I was trying to say is it's not clear to me what is the best way to do so. Like, is it just easiest just to go through this CMC SH gauge approach and using the elliptic hyperbolic system that you get there, or should we really go back to Todd's Fuchsian method and try and kind of adapt that? It's not clear to me yet what's the best one to do.
And the second, I guess, sort of related question that I had was that so certainly Speck and Rodyansky and Speck do it on the torus as well. Is there an example of study of Einstein-Euler where people consider just flat infinite space?
Oh gosh. If anyone knows, I'd be happy to hear. As I said, I'm not entirely sure of the literature. I don't think so. And also they're in, I think also in some sense they're in the accelerated expansion regime, so they're not so worried about that.
Mm-hmm.
So
it wouldn't make a difference probably.
That's
right?
it. It wouldn't make a difference. So I think the answer would be no, but that's just because of what people have considered, what kind of scale factors people have considered so far.
Okay, thank you. So basically you're saying that there shouldn't be a problem considering.
Yeah, and like in these, I must say, in some of these papers by Speck and Rodyansky, I'm sure they make the comment that they just take T3 for simplicity and they don't see there being an obstruction for doing R3. I feel like I've read that somewhere, but I could be mistaken.
I mean, from what I remember, they said that this means that they can consider any compact space, but they don't make, at least Speck doesn't make a comment about infinite case. But
okay.
Sort of,
yeah, maybe there is a difference there. Yeah.
Okay, thank you.
Okay, thanks a lot for the question. So we have Annegret, one question. I think then we have to go to the next speaker.
Well, I just could you just quickly say, so what if k is greater than 1/3, you would expect instability, I guess, but I'm not quite sure now about the previous works that you have mentioned in this direction. So you had mentioned Speck's work of 1/3, but what is there more known about this already?
You mean you mean this case here, kind of if we go above 1/3?
Yeah, exactly. What is the result exactly there? And is it expected to be unstable or only in
Right, yeah, so I think there's a paper by Rendell where he conjectured, or he had numerical evidence that you get an instability when k was bigger than 1/3. I think you always need it to be less than 1 for the speed of sound to be less than the speed of light. And so I think it's, yeah, so Todd is showing that doesn't hold true, at least between 1/3 and 1/2, but certainly the region between 1/2 and 1 is still open. If that answers your question.
Yeah.
Having said that, I should just say, I think there's the paper by LeFloc and Way, where they look at this Chaplin gas. I was reading somewhere there that they, in some case, actually in this equation of state, they do have the speed of sound equaling the speed of light. So in that instance, they are kind of at that critical point of what they call a stiff fluid. But I mean, it's a different equation of state, so it's quite a different.
Yeah, then you have I have a piecewise equation of state that's different.
Yeah.
Okay, so I'm sorry to interrupt, but we have to go to the next speaker. Thanks again, Zoe, for the nice talk.